This is a little bit away from my normal field, so I am a regenerative medicine specialist really, rather than a B12 specialist. I work, I suppose in regenerative medicine our whole purpose is to restore function. So we take a disease situation and we use whatever we can to restore the function back to, for want of a better phrase, a healthy environment. So I came to B12 as a patient, and my interest really starts from a patient perspective as to why do we have such varied symptoms? Why do they vary so much from patient to patient? And I think really importantly, from a scientific point of view, the symptoms we have and the vast array of them shows just how many systems and how many cells in the body are affected. I was also very interested, the level of B12 in the system doesn't really seem to have massive impact to the severity of the symptoms that we experience. And there isn't a standard disease progression. Generally, when we look at a disease from a scientific perspective, we'll find a standard disease progression, we'll find where we can potentially intervene, and then we'll redirect, hopefully, the disease into a healthy body. There isn't really anything standard about this disease, and I think that's because we just don't know enough about the basics scientifically. Despite this, we seem to have a standard treatment. I say standard in terms of if you're under the care of your GP, which has been spoken about this morning. But if you are treating at home, if you're self-treating, you've then got this addition of different types. So you've got methylcobalamin, you've got your hydroxycobalamin, you've got cyanocobalamin. There's all these different options. And we got a lot of anecdotal evidence as to patients feeling better, feeling less symptomatic in certain areas with different types of B12. So I suppose that was my interest. Could we put something scientific behind this to try and understand and give it a little bit more weight as to why we do this? So I'm keeping it very light on the science. So hopefully, basically, this is the fundamentals you need to understand to get hold of what we've found. So B12 is taken into the cells, are taken into the body by cells lining the intestine, and these are epithelial cells. We have lots of different cells in the body, and I'm going to talk about a couple of different ones and the locations of them and why I felt they were important to look at. Once it's in the cells, it goes in to different processes. It's either converted in the mitochondria, which is basically a battery for your cell. It's the power plant. It's where the cell gets all its energy from. And in there, it's converted to adenylyl B12. It can stay in the cytoplasm, where it works as methyl B12. And the cytoplasm is literally the liquid within the cell that supports all the different organelles, we call them, but they're basically the different functional units of the cell float within this cytoplasm. So when it's there, what does it do? Well, within the mitochondria, the adenylyl B12 is a cofactor, so it helps produce something called succinyl-CoA, which is essential for the generation of the energy in the cell from your proteins, your carbohydrates, so basically your dietary intake. In the cytoplasm, the methyl B12 produces methionine, which is an important amino acid. When you think in amino acid, think Lego bricks. Basically, you hear a lot about amino acids. They are the building blocks of the body. So think Lego bricks. There aren't that many of them, but they build together. They give us proteins. Proteins give cells. One of the key things of methionine is blood vessel formation. Now, to have healthy tissue, it needs a supply of food and it needs to be able to get rid of waste. It happens through blood vessels. So if we lose the potential of our body to form blood vessels and to keep healthy blood vessels, we increase the chance of disease, we reduce the function of the body. So this can pretty much be anywhere in the body. So hopefully, key take home so far, we've got different types of B12 in the body, and they work in different parts of the cell where they have different functions. To me, that if we understand that as a core thought, the next question is, well, do all cells behave the same way then? So Do cells from different locations in the body behave differently? Could this be why our symptoms are so vast and are so different? Well, we looked at 2 different cells for our very first study to try and answer this question. The first cells are white blood cells, and they're inflammatory cells. We chose these really because pernicious anemia is an autoimmune condition, which was mentioned earlier. So what this means, your inflammatory cells normally and your immune cells normally help you by defending you against viruses, against bacteria. When we get a disease that's autoimmune, basically it starts to recognise your cells as invaders. So I suppose think friendly fire. You're under attack from your own. But because of that, because it's in the blood, it's systemic. So it can affect absolutely everything from your toes to your fingers, anything that has a blood supply or lacks a blood supply because of the lack of the blood vessels. The other cells we looked at were the actual cells, the intestinal epithelial cells that actually absorb the B12. So this was basically our local response. So how did it affect the specific local cells? And I'll start first with the systemic response because this is sort of feeds into a lot of my other work and sort of where a lot of my interest lies. So we used the macrophages, which are one of the major white blood cells. And they're a really big player in any kind of immune response. In both cases, the cells were chemically activated, so we didn't use cells that were happy and healthy. We actually gave the cells a chemical stimulus to make them aggressive, to make them unhappy, basically. And then we treated them, so we did that for 48 hours. We then treated them with the hydroxyl B12 and the methyl B12. And interestingly, and unexpectedly, if I'm being honest, they behaved completely differently. So we looked at markers of a specific, it's a cell surface marker that basically, if it's expressed, it shows us the cell is in an aggressive phase and wants to create more damage and keep creating damage. There is a purpose in it physiologically. You know, it's there to, if you cut your hand, you need to clean the wound. These cells will go in, they'll aggressively get rid of the bacteria. They then move into a different phase where they heal. Interestingly, the hydroxyl B12 reduced the expression of this marker. So basically, it reduced the aggressive nature of the cell. So you can link this to your inflammation, you can link this to your joint pain, your stomach pain, your general feelings of fatigue. So, first finding, we had a difference. We also found that the hydroxo increased mitochondrial activity, which leads you to believe the hydroxo is working down the adenosyl route and not down any other route. It's not to say the methyl B12 didn't do anything, it's not a simple system. There are lots of routes to inflammation. The hydroxo B12 directly acted on these inflammatory cells. The methyl B12 was more of an indirect route, so there's a lot of chemical messengers when cells talk to each other, and basically the methyl B12 mopped up the ability of the cells to speak to one another, which again reduces the aggressive nature, because if they're in an environment where they believe they're under threat, they will talk to the cells around them and say, right, this is what we need to do. And they work en masse. If you remove those signals between the cells, your aggression's reduced as well. But it's a different route, and different routes will give different different symptomatic pictures. So far, cells respond differently to the different types of B12. Do cells from different locations respond differently to B12? Well, I mentioned we looked at the gastric cells, and my apologies, I don't have pictures, so I'm going to try my best to describe them. They are, we call them a cobblestone morphology, pretty much like the cobblestones you would walk on. That's how a gastric cells, they're little squares. They sit very closely to each other, and they line your intestines. And they act as a barrier, a functional barrier, so they let in what they need, they keep out what they don't need. And basically, when we gave them the aggressive stimulus, so the stimulus to make them diseased, they started to shrink. And in shrinking, they reduced their what we call cell-to-cell contact. So they lost this cobblestone look, and they just started to look round. In the laboratory setting, you think, well, that's fine. In a clinical setting, if that's happening, what you're actually doing is reducing the amount of barrier potential it has. So you're really changing what the body's taking in if you're increasing more gaps in this area. When we gave the same B12 treatment, we saw that equally in both B12 treatments, which was the interesting part, there was no difference. The cells started to revert to their original cobblestone formation, so they were getting back this functionality. In all cases, we treated for 48 hours because of the nature of the cobalamin. And that leads us to our next sort of portion of the study, really. What we need to be able to do is have the cobalamins around longer to be able to see if this impact can be exploited towards actual, I suppose, an actual result. So we've been looking at hydrogels. Now, it literally is like your jelly you make at home for kids' birthday parties. It is 90% water, and it's a very, very loose matrix inside. So there's loads and loads of gaps, which is great for us because cobalamins are big molecules. So what we can do is we can entrap the molecule within the jelly. The jelly, for want of a better phrase, that we use is based on a blood clot. So the body's used to it, there's no toxicity, it can dissolve quite naturally and the body will help it dissolve. The other good thing is it dissolves easily. Now if you think about the aim we're trying to achieve, we just want to hold it there for longer. So if we can put something in there that is quite, I suppose, unstable, which you would normally take as a bad phrase, but it is quite unstable, as the water is removed, and it starts to, the whole gel starts to dissolve, what it actually does is releases little parts of the B12 that's entrapped within it. So we get a slow release. So far we've trialled it with hydroxy B12 and methyl B12 separately, and we can get the gel to form. We can entrap the B12s. At the moment we're looking at tailoring it, so at the moment we can get to about 12 days. They're still in the lab running at the moment, so at the moment we can get to 12 days. I would say we can deliver about 20 micrograms per day of the B12, which is a much more physiological approach. Basically we want to mimic the dietary intake. We don't want 400 times the dietary intake every 3 months because the body doesn't like feast and famine, it kills things. So the aim is to tailor the gel to deliver the right amount over a set time scale. But we need to find out, once this is done, can we still use the vitamin? Is it, you know, can the body still recognise the B12? Can it still work in the same way as it did previously? Our longer term aim is to deliver the recommended daily amount of B12 over a long term. I've put 3 months. We don't know what the potential is. We could get up to 6 months for a self-injectable subcutaneous gel. So that's what we'd like to be able to develop. The ideal would be longer term to mix the types of B12 to make it really personalised to the patient. So if you have more systemic response, we'll put an increased proportion of hydroxy. If you have a more localised response, then you'll have a larger portion of the methyl. We're still working, we're about to start working on the other cell types associated. So we haven't done any neural studies yet, but they're next. So yeah, it's a little bit of hopefully where we'll go in the future. And I hope it made some sense, but any questions?
You mentioned in this gel injection potential.
Yeah.
How is that different to the injection we've got available at the moment? I'm not quite too sure. I can see it's going to be more like a slower release.
Yeah,
natural releasing sort of.
So basically the gel would be injected subcutaneously, but instead of you injecting 1 milligram per mil, which is lost within, I don't know, I think it's, I'm going to get my stats wrong, I think it's about 66% excreted in the first sort of 2 to 3 days. What we're looking at doing is releasing a tiny amount. So the gel, you would inject the gel, you'd inject it as a liquid and it would gel under the skin. So it wouldn't be painful, it would gel when it gets into situ, on the temperature of your body would make it gel. What would then happen, in the same way a body degrades a blood clot, the body would release enzymes. These enzymes break the bonds, and as the bonds break, little bits of it disintegrate. As it disintegrates, it just naturally releases the B12. So you get a very slow, steady release. So we mimic the dietary release, which is what a healthy body would use normally. So that's really the interest is being able to tailor it. Or from my perspective, it's being able to tailor it to maybe address more the symptoms and personalise the medicine to give us all more control over the condition. Okay.
Very interesting. I was just wondering, is this being considered then as a maintenance treatment as opposed to loading doses?
At the moment, I don't think it's being considered anywhere. This is all in the laboratory. So this is all if we could do this, then I would run it alongside, my preference would be you'd run it alongside loading doses. I think you're always going to need loading doses, if only to relieve the initial symptoms. But I think if we can get to a point when someone is stabilised, or even alongside a loading dose, that we can use this, then I think, you know, we get back to what the body's ideal delivery, or as close as we can to it. You know, there's an awful lot of knowledge about receptors, and if you flood a receptor, it can kill a receptor. And if that's what we're doing when we give these massive doses every 3 months, that may also impact as to why, as people get further into the condition, they feel they need more frequent doses, because actually the receptors they've got are possibly reducing. Okay.
I just wondered whether or not the way that you can actually deliver these, whether they're gels or injections, couldn't be done in a similar way to the way that people have insulin injections.
Yes.
Why we couldn't have a pen and then just dial in the amount that we need and do it that way, because it seems to me that nobody's really looking at it. Even with current injections, the stuff doesn't degrade. It's not. It doesn't have to be stored in a particular way. So, you know, is nobody looking at developing this type of pen that could deliver a small amount every day to us?
I think so. I think I would like it to come away from people being tethered to delivery daily. I think if we can have a system that will deliver for us, but I think in perspective of being able, the idea for this is home injection, and there's no reason once we've optimised optimised in terms of exactly which way the hydroxy and which way the methyl goes. There's no reason people can't, as you say, dial in their optimum and inject it at home. It's really stable. From all the studies we've done, until the gels are mixed, they can stay stable as long as they're stored correctly. So yeah, completely, I think it would work. I would like to see it longer term. Ideally, I'd like to be able to do one injection a year. And for that to be, so people, it's not life controlling, and it's not taking up so much of our time.